So we're doing a lab on transformers today, and so as I promised, it's a fairly short lab. The the first part here comes right out of the lab book, and so we have this circuit here where we're going to be applying 120 volts to the primary side, okay, through a series resistor here, which is 220 ohms. And then we're going to go into our transformer, which has a primary side of 120 volts RMS and a secondary side of 12.6 volts. And then we're going to go into the resistor RL, which is our load, right? The L stands for load. So this is our load resistor. And that's just a 10 ohm resistance there. And so then the book kind of asks you to look at a couple of things. One of them here, and I've got this question over here, okay, and that is to specify whether this technically this transformer is two inductors. And so what they're asking here is, right, normally an inductor will throw the current 90 degrees out of phase with the voltage. And so what they're asking you here is that, is there some kind of phase shift due to the fact that this transformer is really two big inductors? Okay. So they're, and again, that just comes right out of the lab, and they're just asking that question. And then they ask you to determine some values. So I just put them in this table here. You have like the voltage on the primary side, the voltage on the secondary side, and we're going to take a look here and see how we can do this. But the idea was that you were supposed to determine from a real transformer in the classroom the number of turns. Okay. And so you were supposed to determine A, or the ratio of primary turns to secondary turns. And then, of course, find the currents and find the powers. Okay. And so, and then the total impedance. And so they kind of walk you through this in the lab. And so, make sure you open up your lab book and kind of walk through that to complete this. And I'm just asking you to kind of fill out this table and to complete that part of it. And then I added just an extra piece here. We talked about, like, in our house the other day. So here is a circuit that I'm giving you. And so we've got, this is kind of like the house one, but in this case, I've got 240 volts RMS coming into the primary, which has 10 windings, to a secondary, which has 5 windings in the top side and 5 in the bottom. So it's what we call a center tapped. So this center tap here is right in the center. So we got 5 turns on the top and 5 on the bottom. So we actually have 10 from the very top to the very bottom. And then notice here where the ground is at on the center tap. So this ground is at the center. Okay. And so when you have a voltage here above your when you have a positive voltage from the top 2 terminals, let me see if I can get some kind of arrow or something here and use as a pointer. Okay. All right. So we have this, so this is our secondary side here. And so when we have when it's a positive voltage on the very top, then then this ground point is going to be more negative than that. However, this this portion of the circuit down here is even going to be more negative. So this is actually going to be negative. So we're going to have like plus 120 volts from ground. From ground here, we're going to be going, say, up 120 volts. And then here, from ground down to here, this is actually going to be minus 120 volts up to 0. And then when you go across the entire thing, then that would be 240 volts. And so we have here then 3 different loads. So this is kind of showing you, the loads that you might have in your house. So I have load A, which in this case is just purely resistive. Okay, and then I have load B over here, which has an inductor in series with the resistor. And then I have load C, which has a capacitor in series with the with this resistor. Okay, and I guess I just realized I was going to change some of these values, but the resistors are all 10 ohms, right? But these two circuits actually have some inductance and some capacitance in them. And so what you want to do then is find, there's a table down here at the bottom of this, and just find, what is the primary current. Now here we're looking at phase angles. Okay, so these are vectors, they have phase angles. So up here we don't really care about the phase angle because it's all resistive. Okay, and so once we answer the question, by the way, the answer to this question is no. Or wait, read the question. Is the secondary voltage in phase with the primary? Yeah, so the answer is yes. So there is no phase shift. So the voltage on the secondary side is in phase with the voltage on the primary side. Okay, because there is no phase shift through the transformer, at least an ideal transformer. And so these on this table here, I probably should have said that, but these are magnitudes only. Okay, because the phase shift is simply 0. Okay, but now when we get down to the second one here, since we have this inductance in the circuit and we have capacitance in the circuit, then we definitely are going to have some phase shift. And so what I'm asking for you to find then is currents and impedances and actually even apparent power. So remember, P is real power and S is the apparent power. Okay, and so I'm asking you to just kind of find these values and fill them out. Now, some of them you can just build the circuit in the software and put some voltmeters or whatever on it and measure the voltages, and then use Ohm's law to find the current or things like that. But some of the values, like the total impedance on the primary side, you're going to have to do a little bit of a calculation there. But get those values, fill them out, put them in the table here, and then upload this Word document back into the assignment tab here in Blackboard. Okay, so that's our lab for today. All right, so if we look at Multisim then, all right, and so let me just kind of come over here. So, anytime you have Multisim, of course, you have your source. So I'm going to apply a power source, which is an AC power source. Okay, and then I'm going to put in my ground, because you always need your ground also. Okay, so here's my ground. And then I'm going to go to basic, and under basic, we're going to find a transformer. Okay, and so this is just going to be a straight transformer with one primary and one secondary. Okay, and then I'm building the first circuit in there, so I just am going to need a couple of resistors here. So I'm going to need a 220 ohm resistor. And I'm going to need a 10 ohm resistor. And so put all my parts down here, and I'm going to rotate resistor 2, which resistor 2 is actually the load. So I'm going to come to the label, and I'm just going to spell out the word load there. Okay. And so R load, and then this resistor was R1. Okay, let me close this document. I didn't need that one open. And yeah, they just call it R, which I'm going to call it R primary. I don't. It's just kind of generic when you just say R because you got lots of resistors, so it's easy to get confused on which one you're talking about. So this is the primary here, and then we're going to just connect these up. All right. So, but here you see when you put down the transformer, it gives you the turns ratio. So if you double click on it to look at your settings, okay, you know they have some. You basically can kind of come over here and you can put your primary turns and your secondary turns. Well, if you remember, okay, so now notice this is 120 volts RMS at 60 hertz, which is what they're giving us here. But notice the secondary side is 12.6 volts. Okay, so if it was a perfect 10 to 1 and we had 120 on this side, we would have 12 on the other side. But we're not supposed to have 12 on the other side. We're supposed to have 12.6. So our turns ratio is actually a little bit smaller than 10 to 1. So we need to open up a calculator here. Okay. And with our calculator here, let me just make a note here. So we have the number of turns. A is the number. A is your ratio, right? So it's the number of primary turns divided by the number of secondary turns. So we need to find N primary. Okay. So we're going to have and that gives you, okay, so your number of primary turns divided by the number of secondary turns gives you your primary voltage divided by your secondary voltage. And I don't think I really put it in these terms for you on Monday, okay? And so, you know, but that's how we can calculate this. And then this would also give you your secondary current divided by the primary current, okay? So this turns ratio gives you the number of turns, number of primary divided by number secondary gives you the voltage of the primary divided by the voltage of the secondaries, okay? So again, this is a unitless thing. You have volts divided by volts, so the volts cancel out, and so it's just a value, all right? But then for the current is the opposite. So remember, when you're stepping up the voltage, the result is that your current drops by that same amount, okay? So looking at our lab problem here, and again, we were supposed to find this out experimentally. I was supposed to like say, okay, here's this transformer, hook up the circuit, and you know, measure the voltage on the primary, measure the voltage on the secondary side, and see what it's going to be. Okay, and so the general values of what it was supposed to be was 120 volts RMS on the primary side and 12.6 on the secondary side. Okay, so you know, so our turns ratio A, which is the primary divided by the secondary, Okay, but normally we normalize it so that the secondary is 1. And so, A is the ratio of the primary to the secondary. So we take our 120 volts divided by 12.6 volts on the secondary side. Okay. And so if we then punch that into a calculator, 120 divided by 12.6 gives me about 9.5. Okay, so this is going to give me about a 9.5 here. Okay, so it's 9.5 to 1 turns. Okay, and then we can go in and we can add our probes. Okay, and so if you remember, if we kind of come over here and we put this probe here, okay, and then what we can do with this probe is go to the parameters first. I always like to get rid of some of the parameters. So what I'm really interested in here, there's no DC voltage, so I don't care about the DC voltage. And the lab's giving us at this point RMS voltages, so I don't really care about those. And my phase angle, to do the phase angle, you've got to associate it with another one. Okay, and so then now I'm going to take and again, I'm going to go to my label. So I'm going to come over here to general, and I'm going to call this V source. Okay, so it's nice to give it a label that means something instead of the generic values that they give it. So now if we come over, okay, and so V source is my reference. Okay, so I'm going to come over here to this one, and this is going to be V load. Okay, and remember, we're going to check this box and say, this, we want to know the phase angle with respect to the source voltage, right? And so we can hook that up. And then on the parameters here, now I do want to see the phase. So for this second probe, I do want to see the phase shift. Okay. And so now when we play this, then you see we've got 120 volts RMS on this side. Okay. And we've got 5 volts RMS on this side. Okay. All right. So, but notice the phase angle is in micro degrees, which means that, micro degree, if you try to measure, 10 to the minus 6 degrees, it's virtually 0, right? It's really, you can't measure that. So, but the other thing we really need to do, you might say, well, why is that 5 volts? Well, remember, there's a resistor over here on the primary side. So if I stick it over here, if I make a copy of this and put it there, okay, doesn't seem to be updating here. V RMS is 96.5 volts here. Okay. So, I don't know, something seems a little weird there. Okay, we should have 12 volts on the other side here. So, all right, so my voltage from the source is 120 volts RMS. And then when it goes through this resistor, we're losing that. And then when we bring it through the transformer, okay, transformer is supposed to be 9.5 to 1. right. All right, so we're basically dividing. We've got like 95 or 98 volts here, and we're dividing that by 9.5. Okay, so 98 divided by 9.5. Okay, should be giving me 10 volts on this side. So I'm not quite sure where my voltage drop is at. Core, it's an ideal core, no leakage inductance, and no resistance. Okay, so this is one thing that's nice about this software is you can actually simulate a real inductor. So you can set that says, oh no, it's going to have some inductance in it. So with the ideal core, there's no inductance. With the but if you go to a non-ideal, then you can specify how much inductance is in there. Then you can talk about the leakage inductance. We kind of mentioned that. And then, of course, you got the resistance and the coil in your coils. Okay. And so you could actually simulate all that. But I've got all that turned off. So I'm trying to figure out why my voltage here is only half of what I'm expecting, about 10 volts. And I'm only getting half of that. So I'm not quite sure what's going on. So, but one thing I also wanted to show you with this, so we'll see what this says. If you come over here to simulate, go down to instruments, and one of the things we can choose is an oscilloscope. All right, and so then with this oscilloscope, I'm going to connect the oscilloscope to the primary side, and I'm going to connect it to the secondary side. Okay. You know what, Josh? That's a good question. I bet you've nailed it. Yeah, I never connected a ground there, so that, yeah, I think you probably nailed it right there. Yeah, you do have to have a ground. Now, yeah, I think you hit it right on the nose. I need a ground, and you also have to ground your oscilloscope here. But yeah, so let's simulate this now, and there you go. You've got it. All right. So that, yes, I had thought when I first dumped that ground that I was going to have to make a copy of it, and then I totally forgot all about it. So good catch. So yeah, you got to have a ground reference point, and so um, I'm surprised it was reading anything now that I think about it, because why was it reading 5 with no ground? I'm not quite sure, but yes, good point. We definitely need that ground. Okay. So, but anyhow, why we have this oscilloscope, because I wanted to show you this. And so you've got this oscilloscope going here, and so we can view the sine waves. Okay, and it's 60 hertz is kind of slow, so that's why it seems to be. And so what I like to do is step it out a little bit, and then this one here is the primary side. Okay. And oh, one thing with the oscilloscope, I think I may have shown you this, but if you come over here, if you click on right click on a trace, you can change the color of it. You can go to segment color and change a trace of it. And when you're using the oscilloscope, that's very, very handy, because then you can apply a color, and then that color will appear on the oscilloscope. So when you simulate it, then you can see the difference. Supposed to here. I guess you need to make sure that the segment color, I think, is going all the way over to the scope. Okay, so you see that color there. I think that's why it wasn't actually showing. Yeah, there we go. So there we've got the green color, and then we've got this one here. And then if we just pause the simulation, then we can see the red is the channel B, which is only 5 volts per division, and channel A is 50 volts per division, right? So now remember, this is peak to peak. When we're looking over here, we have 120 volts RMS, which is the supply, but I'm not reading the supply. I'm reading the voltage here, which is like 96.5 RMS after the resistor. That's what the green is. Okay, so that's my supply after this series resistance here. But and then you can see the green and the red, and you can see that they're in phase. So we can also see that here looking at this angle, because this angle is saying, you know, micro degrees, or essentially 0 degrees here. And so 2 different ways that we can see that there is no phase shift from one side of the transformer to the other. Okay. So then just to kind of see a phase shift. Okay, so I just kind of want to demonstrate a phase shift. So if we come in here, and they don't really ask you for this in the lab, but I just kind of want to demonstrate this. So what I'm going to do is throw in a capacitor here. Okay, so you got to stop your simulation to add things. But I'm going to just come in here, and I'm going to go to basic. I'm going to add in a capacitor. Okay, and this capacitor, I'm going to make 1,000 microfarads, which is technically 1 millifarad. But most of the time when you see them written, they're written in microfarads, even if it's 1,000 microfarads. Okay, so that's why I'm putting it that way. And so what I'm going to do then is I'm just going to connect this in parallel with this load resistor. Okay, and I'm just going to simulate this again. Okay. And again, you don't see any phase shift here, because look at the voltage. So I'm looking at the voltage on the primary side, and then I'm looking at the voltage on the secondary side. So even though there's a capacitor in here, okay, I'm looking at the voltage on that primary side. So actually, I probably should have taken this capacitor and put it in series, so that I can show you, if we look at the voltage on the other side of the load, or on the other side of the capacitor. See, right now they're in parallel, and so it is changing the phase of the current, but we're not looking at the current right now. So if I take this out, I'm going to rotate it, and then I'm going to drop it in here. I didn't. Okay, and then I'm going to copy this probe one more time, and I'm going to put another copy of the probe on the other side of the capacitor. So when you see this, okay, so again, there's no phase angle here. Okay, you're seeing a phase angle 2.8 degrees. between here and here, that's the current. That's because of the current. Okay, but from the primary side, this is the primary side, and this is the secondary side. They both have 2.8 degrees phase angle shift. Okay, and then this one here is minus 12 degrees. Okay, because it's on the other side of the capacitor. So you can see there's phase shift here, and there's phase shift between here and here because the current is out of phase with the voltage now. However, when you look at these two here, they are not, they have the exact same phase shift. It's not zero, but it's the same phase shift, which means that my ideal transformer is not messing with the phase of the voltage or the current. Whatever it is, that it's that same phase angle in there. So the so you have a phase angle. Okay. So when we look at this here, okay, I have a phase angle with my voltage. The voltage on the primary side is 97.6 volts with an angle of 2.8 degrees. Okay. And so what is the angle of my current on the primary side? Well, my current on the primary side is Ohm's law. We have a resistor right here, right at the corner where it says calculator. I'm trying to point with this. We have 220 ohms, and we know that there's a voltage across it. Okay. And so the voltage drop, okay, so the voltage drop there is 120 volts. So the voltage across the resistor primary, our primary, is the source voltage minus the primary voltage, which I just calculated. Okay, so that voltage then is let's see, 120 angle 0 120 angle 0 times, or not times, minus 97.6 at an angle of 2.80 degrees. Okay, so that is the voltage across my resistor. And so let me see if I got something. I think that guy's not going to help me. Let me see if this window, yeah. All right, so here's my octave calculator here. So I can calculate this. Okay, so we have 120. So this is going to be VR is 120 minus 97.6 times J times 2.8 degrees times pi divided by 180 degrees. Okay. And so that is 23 volts Okay, so it's 23 volts with an angle of minus 11.9. Okay, so that is 23 volts with an angle of minus 9, or excuse me, minus 11.9. Minus 11.955. So when we round that up, it's actually going to be 12 degrees. Okay, minus 12 degrees. Okay, so that is the voltage across this resistor now because I have this capacitor in here. So notice here was my 12 degrees, right? Minus 12 degrees. So the current over here going through this load resistor is in phase with the current going through this resistor here, because that's what I just calculated. All right, I just calculated this here is the voltage across the primary, and so this is the voltage, and it's got a minus 12 degree phase angle. Okay, and that's what the current is going through this resistor too. All right, so there's just a little bit about that, but this oscilloscope is nice if you want to kind of measure phase angles, or you can use these probes. Now remember, this probe here, this first one is just a generic voltage probe. To get this one, you got to come to what they call differential voltage. Okay, and with the differential voltage then, and then you always got on this general tab, you got to assign the phase, and you got to select which probe you're comparing that to. Okay. All right, so there's the lab for today. It's really not that long. You just kind of got to build the circuits up and connect them and read the values, and there may be just a couple of calculations. All right, so is there any questions? You guys already got it done, right? All right, there's only even a few people logged in today. We've only got half the class, so hopefully the rest of them will do that. For the rest of the semester, just as a review of what we're going to be doing here, on Monday, we're going to be talking about three-phase systems. And so we'll kind of go have a overview of three-phase systems. And then I'm going to, I'll probably give you a short homework on that. But there's also going to be the exam 3 next week. So exam 3 is kind of a makeup exam, so you don't have to do it if you don't want to. But if you want to try to increase your grade, I'll take the highest of these first 3 exams, or the 2 highest of the first 3 exams. Okay, and so I'm going to drop the lowest, however you want to say that. But and then the following week, then May 4th, okay, the first week of May, the first full week of May is the final exam, and that's it. So we are almost done here. Okay, and I know I've got to go back through and get the grades in here. I've been spending so much time trying to get labs ready online that I have not looked at grades yet. So this next week, most of the classes are just going to be doing exams. So I'm going to try to use some of that time to get back through and grade these labs and homeworks that you've been doing, and go back through that second exam and grade that. So, but that's where we're at. So we are, 2.5 weeks. So the final will be on Monday. What I'm going to do is, since it's going to be in Blackboard, okay, the final is in Blackboard, and so therefore I'll open it up Sunday, May 3rd, and I'll close it on Wednesday. So you can take it Monday, you can take it Sunday or Monday or Tuesday or Wednesday. But I really need to have you have it completed by Wednesday because I'll have to be submitting grades, to the registrar. So I'm going to have to get through all these grades and everything. So I'll give you about a 4-day window to take it. It's going to be like that second exam was. It'll be in Blackboard. It'll be timed. Okay, so that so once you do it, you have to complete it. All right, but if you want to wait till Wednesday, that's okay. But like I say, once you start it, you'll have like an hour and 50 minutes to complete it. Any other questions there? Oh, okay, so this is the lab here. I'm just going to let you guys go work on it and complete it and upload it, and then you can if you're having any questions, just shoot me an email, and if we need to, we can log back into Collaborate. But I was just going to shut it down for now. But shoot me email, and I'll try to answer you, and if necessary, we can log back into Collaborate. All right. Any other questions there?